Hello, welcome to Group 8 final project, looking at the productivity of the Hankook Tire Manufacturing Facility expansion. For a team introduction, this is the team. My name is Benny Weiner. We have Aditi, Jaula, Owen, Christine, and Felipe. For an outline, this facility is located in Clarksville, Tennessee. The general contractor for the project is Clayco. The budget was $1.6 million, and its timeline, it started construction in the fourth quarter of 2024 and will be scheduled to complete in the first quarter of 2026. The size of this expansion is 2.2 million square feet. The purpose of this Hankook Tire Manufacturing Facility is to expand Hankook's production capacity for passenger cars and truck and bus tires through their new manufacturing lines. This facility also has constructed advanced infrastructure, including equipment pits, and it's using a multi-story mixed building, and it uses automated storage systems to support large-scale operations, which is their largest scale of operation here in the U.S. To continue, this expansion of the facility will also install critical systems such as new HVAC, fire suppression, industrial piping, new electrical distribution, and process controls to optimize safety and efficiency. The purpose of this expansion is to enhance the existing Phase 1 plant with new additions to the building and add a lot of new features that will create a safe and efficient work environment for Hankook.
We chose to observe this project on February 24, 2025 from 1:51 p.m. to 2:54 p.m. We took progress pictures around every 15 minutes or so, which includes 1:51 p.m., 2:03 p.m., 2:16 p.m., 2:41 p.m., and 2:54 p.m. Here we can see construction crew productivity and equipment in action. Some of the current construction activities that can be seen include structural steel erection, exterior facade installation, roof installation, and concrete pouring. For our project, we chose to optimize structural steel erection. Steel erection crews vary depending on the size and complexity of a project. However, a sample erection crew for this project would consist of 9 crew members. This includes 1 foreman, a raising crew consisting of a rigger, a crane operator, and an oiler, a fitting and fastening crew consisting of 2 fitters and a bolter, and a welding crew consisting of 2 welders.
Next, we have steel erection process. Oilers, maintenance workers ensure that equipment is properly lubricated and up to safety standards. Foreman works on site preparation and selecting structural steel column beam for material staging. And next we have rigger. Rigger is responsible for all the material handling operations, and crane workers in charge of setting up the equipment, lifting steel and positioning it onto place as determined by erection drawings. Next, we have fitted iron workers and fastening iron workers. They are in charge of working on steel connections and applying torque to the bolts. Finally, we have welders. Welders are responsible for welding the connections according to erection drawing and structural specifications. These roles are really essential for steel erection process and the construction phases.
This crew balance chart represents initial observations made directly on site during the steel erection activities. It maps out the 60-minute cycle and highlights how each crew member spends their time. As shown, the foreman is highly versatile and involved in multiple tasks, like site preparation, carrying materials, and connecting steel. Iron workers mainly focus on welding and connections, but some were idle for extended periods, especially iron worker number 2 and number 4. The crane operator was fully dedicated to equipment setup and lifting tasks, while the oiler supported those operations by maintaining the equipment and checking on progress. This new crew balance chart represents our first proposal for improving efficiency based on the initial site observations. In this version, iron worker number 4 has been removed from the crew. To compensate, the foreman takes on the welding task, which helps reduce idle time and eliminates the need for an additional worker. The chart shows a better task distribution with the foreman now involved in both welding and general site support. Ironworkers 1 and 2 continue handling connections, while ironworker number 3 focuses only on welding. In this second proposal, we focus on further optimizing the crew by removing oiler positioning entirely. Here, the crane operator takes both the crane-related duties and the oiler responsibilities, including equipment setup and maintenance. As a result, there is no need for separate oiler role, which reduces the total crew size. The foreman continues performing welding tasks and supporting the progress check. Ironworkers 1 and 2 are dedicated to connecting steel, and ironworker number 3 handles all the welding. In this third and final proposal, we have optimized the crew further by removing ironworker number 3 from the team. To maintain productivity, ironworkers 1 and 2 take over the welding duties in addition to their original tasks. This allows the crew to complete both welding and connecting work without adding idle time or overloading the foreman. The foreman continues with site preparation, progress check, while the crane operator manages all the equipment-related tasks, including lifting, positioning, and oiling.
The initial process chart is developed based on the current site logistic and the resources available. Based on the webcam locations, we could easily tell that the main storage area where all the structural steels are staged at is at least 1,100 feet away from the crane. In the early morning, workers use flatbed trucks to transport the structural steels from the main storage to a temp storage that is approximately 50 feet away from the crane. And once the crane finished picking the previously delivered steel, workers can now move the next steel component closer to the crane. For quality control purposes, ironworkers inspect each steel prior to attaching it to the crane cables to ensure the steel being installed are meeting plans and spec. After inspection and cable attachment, the crane operator now can lift the steel into place while the ironworkers guide and install the steel to the main structure. This entire process, as shown on the slide, is lengthy because there are quite a few steps that can be eliminated. To improve the initial process chart, an easy solution that came to our project team's mind is to move the main site storage closer to the area that is currently under construction. This would reduce the amount of flatbed truck deliveries to almost half of their original distance. Although this solution highly depends on the availability of spaces nearby, this is still the most effective way to improve crew productivity with minimum cost impact to the project. The second improvement is to eliminate the pre-pick steel staging area. By effectively using the space adjacent to the crane and organizing each material by installation sequence, another material handling procedure can be now eliminated. The flatbed truck will drop off the steel right next to the crane for inspection. The crane may even be able to pick the steel right off the truck directly. Third improvement is to move the main site storage area even closer to the active construction area. The telehandlers can be now used as the main equipment for delivery instead of using flatbed trucks. Ironworkers can even inspect the steel at the storage area ahead of time and not wasting any time when the crane is actively operating.
Flow diagrams will often be used with process charts to show how materials move throughout a site for specific construction activity. The current flow diagram for the chosen steel erection crew is shown here. The steel starts in the main site storage location, a parking lot on the other side of the site. Each piece is then taken to a temporary storage area approximately 1,100 feet from the main site storage. When the steel is about to be installed, it is then taken about 50 feet to a staging area near the crane. It is then moved to the crane before it is inspected, picked up, moved to the installation location, and then installed. First proposal to improve the installation process would be to move the site storage to a more central location so less time would be wasted moving the steel. We think this would be around 500 feet from the temporary storage location instead of the past location where it's 1,100. The second possible improvement to the flow diagram is to get rid of the temporary storage area and instead just move the steel that will be installed in the near future from the site storage area to the staging area. This will reduce the amount of movements needed for each piece of steel. The final possible change would be to create a separate storage area for the steel from the main site storage that is much closer to the installation location. The other processes cannot be changed as much as the locations of the storage area and what is stored at each one. For example, moving the crane closer to one installation location would only move it further away from another, resulting in little to no change in the efficiency of the operation. Changes to the steel erection process will result in either less manpower and equipment being needed, or less time will be spent moving the steel. With the distance between each material movement and the number of movements decreased, the same worker will be able to move more in a single day than before. This means that they may have more time available to help with other activities around the site, or less workers and equipment will be needed to complete the same task than before, decreasing the cost of the process.
Thank you for your time, and this concludes our presentation. And here is all of our references, including a link to the webcam that we have been observing.